Okay, this is video number 36. It is about a specific type of wave, and that is a sound wave. Sound waves are compression waves or longitudinal waves traveling through various media. Air is the one we are most concerned with, and they're created by objects that are vibrating in air or other materials. But again, air is the one we're most concerned about. So like a speaker shaking back and forth will create pressure waves rippling through the air, which travel out and reach us, and most of us are then able to detect those pressure waves through our ears. There are two very specific things I'd like to talk about with sound waves. One of them is beat frequency and one of them is Doppler effect. Otherwise, sound is just treated like any other wave. So let's start with a beat frequency. I'm not going to play this video for you. Again, this is a demonstration I would typically do in class for you, and I don't have the equipment to duplicate it here. What I will ask you to do is please listen to the video, because otherwise it will not make sense when I say to you that the beat frequency is what happens when you add together, or rather superimpose, two waves that are nearly identical in frequency. If they're nearly identical in frequency, then when they add together, you sometimes find that they add together in a constructive interference pattern and sometimes in a destructive interference pattern, and the difference between the two can actually be detected as a wave itself. So for example, the red wave and the blue wave here are being added together to form that bottom wave that is, I guess, magenta-ish. And you can see that sometimes the magenta wave is very large. That's constructive interference when the two are in phase. The red and blue are peaking at the same time. But they're almost the same frequency, which means sometimes the red is peaking while the blue is troughing. And that's where the magenta wave becomes very small. So while the red wave and the blue wave are relatively high frequency, and we might hear those as high-pitched sounds, this magenta wave has this very large waveform. Don't look at the individual waves like this on the magenta, but rather the larger sinusoid shape. That is the beat frequency that was described in the previous video. So when you hear it, you'll know that this equation that's given on the left here, the absolute value of the difference between these two the red and blue frequencies here, will generate what we call a beat frequency. And how quickly the beat frequency or rather how frequently the beat is heard is that simple function right there. All right, let's take a look at what the Doppler effect is. The Doppler effect is a very familiar phenomenon, but I want to make sure that you have not misunderstood it, because occasionally people misunderstand and they tell me that the Doppler effect is that an object gets louder and then quieter as it approaches you and moves away. That does happen, and that is not the Doppler effect. The Doppler effect has to do with the relative motion between the source of a sound and the observer, and therefore a change in the perception of the frequency of the sound or other wave. So if the source of a wave is stationary, which is how we'll usually talk about it in this class, then the wave that is generated travels out evenly in every direction, as it says here. But when the source of the wave moves, then it changes how the frequency is perceived in different directions around it. As it says, it's very helpful to think that the source of the sound is chasing its own sound waves, but it can only do that in one particular direction. An animation coming up might be really helpful. Because it chases its own wave, it means that an observer in the direction that the source is moving, toward, will hear, or in other ways perceive the various waves, hearing in particular for sound waves, will hear the waves more frequently than they were generated. And if the source of the wave is moving away from you, then you will hear the frequency less frequently than it was generated. This is not an illusion. You actually do perceive the frequency to be higher or lower, because it is, due to the motion of the source. This is how OpenStax draws it, and you can see this is a vehicle moving from position 1 to 2 to 3 to 4 to 5, and so it looks like it's chasing its own sound waves. That's what those gray circles are the sound waves emanating out in all directions. So the person at point X is going to hear those sound waves more spaced out than the person at point Y. As those circles grow larger and larger and larger, they will reach point Y more frequently, more scrunched together, and point X they'll be more spaced out. This drawing is to demonstrate that this is also possible to produce this effect by having the source of the sound stationary and have the observers moving Definitely possible, not as common, but we'd like to at least mention that it can happen. This video, which is another one that I'm not playing, is fantastic for demonstrating that the person in the car playing the trumpet does not hear a change in the pitch. For them, the sound is constant the entire time. However, in this video, the person playing the trumpet sticking out the passenger side window of the car here drives by a school where a bunch of students in a high school physics class are on the side of the road to observe what happens, and they hear the trumpet, and they definitely perceive it differently from the person recording in the car. So this is another really good one. It gets really loud. I recommend listening to it. It's an excellent example of Doppler effect that I don't want to subject you to in the middle of this. This animation is an excellent demonstration also of what's happening. So the one thing about this animation that's a little silly is it makes it look like the ambulance here is driving as fast as the sound waves, so 340 meters per second, which is a little ridiculous. But the idea is the same, and you can see that that sound wave in the blue box is stretching out now. That is representing the perceived sound for the person who's standing there. So let's maybe run that animation again. The ambulance is generating this sound and then chasing its own sound waves forward, and so they're going to, all those sound waves are sort of stacked up, and they're going to be perceived by this person standing there very suddenly. And the more frequently the wave strikes you, the higher pitch is how we perceive that. We hear that as a higher pitch. And then as the ambulance moves away, it's heard as a lower pitch. I gotta be honest, I like the train and the trumpet a lot better. Most textbooks and instructors like to talk about police sirens and ambulance sirens and fire truck sirens as good examples of the Doppler effect. And they are, but I kind of don't like the siren example because the siren pitch is changing anyway. I really like the train and the trumpet because they are producing a constant pitch. It is just a steady pitch, and then it's really obvious that the change in pitch is because of the motion. OpenStax gives you two different equations as part of their explanation for the Doppler effect, and the two different equations are based on whether the observer is stationary or the observer is moving. I will give you the first one on our equation sheet because the first one is the only one that I would potentially ask about on the test. That's not a guarantee, but I am telling you that I won't ask you on the test the version of it where the source of the sound is stationary and the observer is moving. All right, that's all I have right now for sound. Please do watch those videos that I linked, and they're in the notes. And I will come back with example problems in the next video.